Then we will go to the, let's say, subject of the talk, the DC multibus. We will show a mathematical model of it. Then we will present a couple of different control algorithms to deal with control targets. And after that, some numerical results that validate the performance. And finally, let's say brand new, fresh, preliminary experimental results that we've been working on in these, let's say, last weeks. And finally, the usual conclusions. Okay, so Arnau and I belong to the Advanced Control of Energy Systems research group, in which our, let's say, main feature is multidisciplinarity, in the sense that we are mathematicians, physicians, engineers belonging to different departments of UPC. Our group is relatively small. We are 8 seniors, and our headquarters are at the Institut of Industrial and Control Engineering here in the engineering school. So our main interests, as you can see, are focused on modeling and simulation and control of complex systems, and especially interested on energy-related fields, in particular in electrical quality and automotive applications. So our research is mainly applied, although from time to time we make let's say modest contributions to modest theoretical contributions. In many cases, most of them triggered by the applied problems we deal with. We also do some technology transfer, less than we'd like, but well, we're working on that. As research lines, all of it goes around advanced nonlinear control techniques. Well, linear and nonlinear, let's say advanced control techniques. In the linear case, we use resonant repetitive controllers to deal with periodic references and disturbances. Also with nonlinear control techniques, adaptive sliding mode, energy-based, non-multisystems, complex networks as well. And if the mathematical model is a large-scale system and we cannot handle it, we also try to use model reduction techniques to cope with it. All these, let's say, lines are applied to or are focused on these research interests that I mentioned before. On electrical quality, we are basically interested in generation, conditioning, management, and storage of electrical energy, in particular stability of power networks, especially those feeding constant power loads. Also in the modeling and control of DC-DC and DC-AC converters, control of electrical drives, and also on automotive systems, in the electronics of hybrid and fully electric vehicles, so battery chargers, electrical actuators, stability of the in-vehicle microgrid, sensorless control of permanent magnet synchronous machines in the electric vehicle powertrains. We also have some works on vehicle dynamics, and finally on autonomous driving, in particular traffic flow analysis and cooperative adaptive cruise control. And it's in this automotive field where the presentation, let's say, frames. In fact, this is the image we chose for the presentation, and that the research is funded by a national project. This would be the who and the what we do. How we let's say face control problems. That's the goal of this slide. So the idea of attacking control problems is usually the same. We will have a plant probably subject to disturbances with an output that is expected to follow a certain reference, and to do this let's say we count on an appropriately designed controller. Now, the steps we follow are the ones you see here. We start by a modeling phase in which we aim at obtaining a mathematical model of the system which is accurate enough to capture the main dynamical features of the plan, but also simple enough to allow us making conclusions on, let's say, theoretical analysis, theoretical proofs of stability, of robustness, whatever. So once we have the mathematical model, we go into the design phase, in which we design a controller and we carry out a closed-loop analysis, trying to see if the performance we are getting is the expected. And this goes in an iterative way until we produce the best, of course, the best up to our capacities controller, which is then validated first numerically, so as not to break anything. And once it's working in silico, then we go to the lab and try to implement it. So this is the way in which we will, let's say, attack our problem. The idea behind is that the increasing electrification on vehicles that we're seeing nowadays entails issues related to the onboard microgrid, which are mainly related to stability and optimization algorithms. So in order to deal with this, we consider a DC multibus converter capable of delivering the most commonly used voltages in automotive applications, which are the 400 volts for the powertrain and the 48 and 12 for the auxiliary devices. Let's say the advantages of our proposal or design is that we are working with just one storage element and just one power converter, and so we can have size and weight reduction. If we had to work with three, the situation would be, of course, different. Then the DC multibuses are connected by a magnetically coupled multi-port DC-DC converter. So in our case, we have a 3-port high-frequency transformer here with a full bridge converter, 3 of them, and a capacitor in each port side. And the goal here is voltage regulation with robustness to resistive load disturbances and uncertain constant power loads. So, in order to derive the mathematical model, we assume that we have been indeed able to achieve a constant voltage for the 400 bus, and we have here the average model for the 48 and 12 voltage buses, which are the ones we have here. In this model, the control outputs are the bus voltages, V2 and V3, which you can see here. Our control inputs are the theta 2 and theta 3, the phase shift of the modulated voltages. Of course, the control goal is to set this voltage to asymptotically track in a robust way the references, 48 and 12 volts respectively. And you can see in the model, you can see here the linear loads, and you can see here the constant power loads that we'll try to deal with. So, trying to follow a little bit the control design methodology, we define a first, let's say, I won't say change of variables, but reassignment. So to have the converter dynamics written in a more at least simple way, which would be the one you can see here below. And this will allow us to hopefully better explain which is the control structure that we propose. We will firstly change the control variables because if you allow me to get back, you see here that our control variables, our control inputs enter the system in a quite non-smooth way, so with cross products, absolute values, etc. So in order to at least firstly simplify the design, we make a change of control variables. Of course, this is just a way of kicking the problem ahead, because in the end we will have to revert this change, but in any case, we'll cope with this later. So we'll have our multiple converter with the outputs V2, V3, and these values are fed into the controller together with the references. This controller produces a control law in the U variables that go then through a control law inversion block to get the physical control values, theta 2, theta 3, that are delivered to the system, and of course, everything then expected to work. As I said before, in this work, we propose two control algorithms, one based on feedback linearization, and another one which is a classical adaptive controller. Now, let's go for the first one. In the first case, we change the control variable, and we also change the output variable as it is here indicated. Of course, we are not going into the specific details, just to show you how this works. With this change of control and state variables, the dynamics of the converter become linear, the ones you can see here, linear with a constant disturbance, okay? And with the control actions U2, U3 here. So in this case, we can easily propose a state feedback control law with integral action, which is the one we can see here. The integral action is given by this variable. Notice that the control action gives the system variable z, which is the integral of the error. So this state feedback controller with integral action is, in fact, or can be seen as a PI, as a proportional integral, the usual control law. Okay, so once this is designed, we go to the mathematical analysis, and skipping again details, we are able to prove asymptotic stability of the closed loop system, and in particular, asymptotic tendency of the voltage variables towards the respective references. So, which is in fact what we want to do. It's worth remarking that it's not possible with this control scheme to identify the unknown variables R, K, and Pk, so the constant, so the linear loads and the constant power loads, because to do so we should play with the equilibria of the system, and the integral variable equilibria contains the two parameters. So with just two equilibria for the integral variables, and we are not able to obtain 4 parameters. In any case, the control scheme now is the one we see here. So we deliver the output and the references to the controller. We carry out the change of coordinates to produce the Xi variables, which are delivered to the PI controller, which produces the U variables, and then this goes to the control inversion block to get the physical variables finally fed to the multi-port converter. So this is the essence of the first control scheme. The second one, our adaptive controller design starts with a slightly different control change, which puts our dynamics in the form you can see here. Notice that main features here are nonlinearity, so we are dealing with still dealing with a nonlinear system, and these terms are related to the inversion of the control variable, and may at first appear annoying, but if you see there is an antisymmetricity here in V2, V3, the lambdas and the signs, that in the end will help us in the stability proof. So this in the end will cancel each other and won't be a specific problem. As regards the adaptive control law, this is the control law we're proposing now. This classical adaptive control law could be understood as a nonlinear PI. And I'm saying that because notice that we can see here a proportional term, a term which is proportional to the error. So this would be the proportional part. And then we have these two terms that, if you recall what's going on here in the system, these two terms are expected to cancel out the effect of these ones in the system. And of course, this will happen when the estimators G hat and P hat behave appropriately. For these estimators, G hat and P hat, estimators of the conductance and of the constant power loads, we propose this kind of dynamics, of dynamical evolution. And notice that the time variation of, let's say, G hat is proportional to the error times, in this case, V again. So in the end, what we are putting here is the integral of something like this. And here we're putting the integral of something like this. So in the end, we are feeding the system with a proportional part and a sort of nonlinear integral part. That's the point. Now, with this adaptive control law, we obtained the closed loop system and we analyze its stability. Differently from the previous case, we are only able to prove local stability of the closed loop. Notice, but that in this case, the closed loop includes the estimating variables, G hat and P hat. But despite this local stability result, in what, let's say, refers to the target variables, we can prove asymptotic stability of the target variable. So local stability overall for the system, asymptotic stability for the target variables. Again, in this case, the local stability is now responsible of the fact that the estimators, G hat and B hat, do not necessarily converge to the actual conductance and constant power load values. This is because, again, the equilibria satisfy a certain relation, and from here we cannot, let's say, obtain G and P. If you allow me to get back, I mentioned that the goal of these two terms was to cancel out the effect of these ones. And this is done, but not one by one, but overall. Both of them cancel out the effect of both of them. So, again, the control scheme now, we have the adaptive controller, which gets or receives the references and the output values, produces the control variables U. This goes to the control law inversion block to get the physical control actions, which are finally delivered to the multiport converter. And next slide has to do with the control law inversion. As I said, that these control transformations include highly nonlinear terms, so cross products, absolute values, etc. But in this case, we are lucky. And we are lucky because it turns out that when we plot the transformations, we see that in the region of interest, which is, let's say, the use in the interval not 50 amperes, the behavior is almost linear. And then what we do is to reverse the change of variables using the linear approximation of the change of variables. So indeed, let's say the real or the physical control actions are obtained as linear combinations of the control, or let's say the fictitious control variables U2 and U3. Of course, this in both cases, in the adaptive case and in the feedback linearization case. And of course, this is something that we observe, let's say in MATLAB or in Mathematica, and we don't know if it's going to work or not till we put it in simulations. But it turns out that it works, and we do not observe a specific loss of performance. Now, as regards numerical results, we have firstly produced realistic numerical results using MATLAB Simulink plus Inkscape, and our converter has been modeled with switching and conduction losses in the power switches, with resistive losses in the transformer windings, and also including reactive components. The set of control parameters and system parameters should be here. And as regards plots, we are here opposing both performances. The tests include resistive load jumps indicated here and constant power load jumps in both buses. And we can see that in both cases, both feedback linearization and the adaptive one, we have the expected results. So once we have a jump, the recovery is good for the 48 bus voltage, the 12 bus voltage. This one is noticing a little bit more what's going on in the previous one, but in any case, performances are good. And the same for the adaptive controller. Notice that here we have it a little bit more oscillating, but we would say that performances are quite nice. The control actions here depicted, both for the feedback linearization and the adaptive, are not saturated and are within bounds. So these are phase shifts, so it should be between minus pi over 2 and pi over 2, which is fulfilled in both cases. The output currents also behave. And this final plot just tries to depict the behavior of conductance and CPL observers for the adaptive case. And we have not plotted the references because for scaling reasons we couldn't. It was not. We couldn't see it nicely. But in any case, this confirms or tries to confirm that the theoretical prediction of the impossibility of having the conductance and CPL estimators stabilizing at its, let's say, references. Well, and finally, the experimental results. Here you can see the proto we have built in the lab with magnetic core, the 400 bus. This is the back side of this, where you can see the 48 and the 12 volts bus. And we have here the microcontroller, and here the signal acquisition board, which is an unknown design, let's say. This is, of course, it's over-dimensioned because it has multiple channels to for signal acquisition, and we use it not in this application but in other applications. Okay, and the oscilloscope pictures. Notice that for the feedback linearization case, we have performed a couple of experiments. The first one with a 12-volt bus with 1 ohm resistive load and introducing changes in the 48-volt batch in the 48. Starts with a 3 ohm resistive load, and then we connect 1.25 kilovolt CPL at this time instant, and performances are as good as theoretically or numerically predicted. In this case, notice on the right hand side, we have the 12 bus that goes from 1 ohm resistive load to open circuit. The 48 volt bus stays, and again, nice recoveries. Experimentally fine. In this case, we see that the control is decoupled in the sense that changes at a certain bus do not affect the other bus. We saw this numerically for the 48 bus. We see it here for both of them. Well, that's it. Efficiency up to 95%, and voltage drops not too high with nice recoveries. And for the adaptive control, same experiments, almost same results from a qualitative point of view, maybe a little bit more oscillating here, as you can see. But as I told you, these are preliminary experimental results we have just obtained in these precedent weeks, and probably we have to work on more carefully in the tuning of the parameters. But in any case, that's it. We have again robustness, same efficiency, and these voltage drops and recovery times. And that's it. So just to conclude, we have presented adaptive and feedback linearization-based controllers for a magnetically coupled multi-port DC-DC converter, with main features being asymptotic voltage regulation and robustness in the face of resistive loads and constant power loads. The design included nonlinear control transformations that were inverted using linear approximations with no power losses or no significant power performance losses, and all this was numerically and experimentally validated. So that's it. Thank you for your attention, and I don't know, Ignacy, if you introduce the questions.
Thank you very much. That was exciting, especially for those people who are able to follow the math, which I confess that for some of us, it's sometimes it's difficult, but it is clear. Also, I have to say to the audience that the talk has been given by Josep Maria, but Arnau Doria is behind the screen also, willing to provide with some answers that people may have. And if you have any questions, I would suggest that you just jump in and turn on your microphone and ask the question. If we see it's messy, we will request to request the word by the chat. Any questions? Anyone who wants to break the ice? I people who know me, even not being a host, I love to break the ice. And my first question is the following: as far as I have been able, not being an expert on the topic, of course, but as far as I have been able to follow what you talked about, I see that there's an immense amount of possibilities to apply this system that you have just explained to us. Of course, I would like to know how different would it be to consider this system if we, instead of thinking of a vehicle where we have 400 volts for the power engine and 48 and 12 for the auxiliary systems. We were thinking, for example, of a house that might be powered by a fuel cell, or a spacecraft that might be powered by solar cells, and that also would benefit greatly as far as optimization is concerned from the from having these different ports with different outputs. Do you think that systems like this can be applied to things like that, or is this question just showing my ignorance on extreme that it's unanswerable?
No, I can ask if you want. You can apply this kind of systems in multiple applications. Of course, it will depend on the application, that the topology of the power converter. So it means that the circuit that Josep Maria showed in the previous, one of the first slides, you have to modify it because, for example, in a house, the devices that you connect in the house are single phase or AC devices. So you have to modify the power converter, also all the circuits there in order to provide this AC voltage. Okay, so for example, in a spacecraft, or you mentioned also some mobile vehicle applications, then you have to take into account the weight, also the size of the power converter or the topology of this. So each application requires, let's say, its own design. Okay, so you have to be careful where you will place this device, so this system.
Thank you. Now that the ice is broken, contribute to melt it a little bit more. Well, I have another question.
I can add some comments on the work that Josep Maria presented. I think it's one of our main advantages of being a multidisciplinary group is that we can go from the application and then we can go back or go down until the math problem. So writing the equation, all the equations that Josep Maria showed in the slides, and then come back to the real application, so the lab prototype, and then to obtain experiments from the real from a real device. Okay, so I think it's one of the advantages of working together, mathematicians, engineers. I think it's this multidisciplinarity that is easy for us to go to the theoretical problem to the application problem. And okay, we have our background, so we are experts in our part of the problem, but we can easily talk about our problems and to solve the problem from the beginning to the end. So I think it's one of the main characteristics of our research group.
Okay. Yeah, well, my question was, it's a very general one, but imagine that I am a student. Imagine that now I am 23 years old, which I'm not very much. And I am good at math, and I always had an interest for mechanical engineering or for electrical engineering. And I say, well, I would like to explore things like that. What would you recommend students, like many of those we have at our university and other universities, how could they get started in this thing little by little without being so impressed by the number of circuitry and equations that you put on the screen? Do you have students working with you? Do they contribute with research? Or if you don't, how would you recommend students with an interest in that to get involved with this kind of topics?
Josep Maria, me?
Well, you started with the replies. Maybe you.
Okay, so I think the first question that we ask to the student when he arrives or she arrives is what you are interested on. So this is the first question. So maybe we can start showing which are our fields of interest, and we show equations, we show simulations, and we show the lab. So this is the big picture of our group, and then we say, okay, where you will be more comfortable, writing equations, running simulations, or in a lab, assembling a circuitry or something like this and getting real experiments. And from here, then you can put the student in a right place. Okay, there are students that are more interested in getting experimental results. So this is a typical engineer student, but we are in contact also with the Facultad of Mathematics and also the Ingeniería Física, so physics engineering, and they are more interested maybe in equations and to solve these more theoretical problems. So this is the first question that we ask to the students when they arrive. So which part are you interested? And of course, then you can move or you can share, from the theoretical to the simulation is quite easy. It is just writing a program and then run some simulations. And from simulations to experimental part is also quite easy to, at least to taste for them. Yeah.
Very good.
Agree.
Any questions? I not in this topic, but some years ago I did kind of a game. I had two students who were interested in the same topic, and one of them was more on the theoretical development of things, another on the experimental. So I gave them the same thesis topic. It was a master's thesis. Mm-hmm. And I didn't tell them anything. And then, of course, a couple of months later, they realized, they came to talk to me, and they were very upset, saying, well, you have given us the same thesis topic. And I said, well, you have successfully passed the first step, which is what the other one is doing, And now, from now on, you can collaborate. I think these multidisciplinary approaches are great, and I really congratulate you. I think it's the way to go, especially in these kind of topics. Are there any other questions from the audience? Which we have a pretty good audience. We have had up to 20-something people, and this is very good news for our seminars, which used to be a little bit more restricted. But apparently, this promotional campaign that we have made is getting to a good port. So thank you very much, Josep, Maria, Arnau. This was for us a very important talk because it was the beginning of a brand new seminar series. And for sure, as soon as we can, we will be more than glad to share a coffee or a lunch or even dinner or a beer, why not, with you. All right. Thank you very much.
Thank you very much to you for the invitation. And everyone